Hi everybody. In this section we're going to look at applications of what we've learned so far in science. So we're going to jump right in. There's some stuff you can read here in the beginning. I'm just going to get to the first example because there's only a few examples today, but they're pretty long. So here we have the position of a particle. We just want to know if we know where it's going to be in a straight line, forward or backward, if we know where it's going to be at a particular time, what else can we learn about it? Right, so how much information can a position function give us? That's actually what we're going to find out. So we want to, first thing is find the velocity. So the velocity is just the derivative of this. Right, the derivative of position is velocity. So that's stuff we've learned before, but we're just bringing it all together. Stuff we learned in various sections. We're kind of bringing it all together. What's the velocity after 1 second? So we're going to take the derivative and plug in 1. And then the next two questions are a little more application based. When is the particle at rest? So think about what that means. And when is the particle moving forward? So let's start with the velocity. So the velocity is just the derivative of position. So you just plug in your position function, take the derivative, so we know how to do that. So this is going to be 3t squared minus 18t plus 24. And that's the answer. Next up, we want to know the velocity at time t equals 1. So just plug 1 in here. So you get 3 minus 18 plus 24, which is 9. So what does that tell us? Well, it tells us that the particle is moving forward at time 1, right, when t equals 1. Next one, when is the particle not moving? So what we do is set the velocity equal to 0 and solve this. So this is a quadratic, so you factor it. Factor out the common factors first, then factor the remaining part. And you end up with t equals 2 and t equals 4. So we're starting to get some information here, right? We know it's moving forward at time 1, and then it's not moving at all at time 2. And it's not moving at all at time 4. So let's see if we can come up with, a way of determining when it's moving forward. So we want to know, when is the velocity positive? So the way you do this is, we know when the velocity is 0. So you just plug in various values. For example, we already know that the velocity at time 1 is 9. So that means that the velocity is positive on the entire interval from 0 to 2. Right? So think about why that's true. This entire interval is represented by this one value, because if the velocity changed direction, this is a continuous function. The velocity is a continuous function. So if the velocity changed direction, it would have to cross the t-axis, which it doesn't do because these values here are the only places that it crosses the t-axis. So we know that t equals 1 is representative of the entire interval. One quick thing to point out, this is a less than or equal to, because if you plug in if you plug in 0 into the velocity function here, you get 24. So it's moving positive at time 0 as well. So it's positive at time 0, positive at time 1, and then 0 at time 2. So that entire interval, but we don't include the endpoint here because it has stopped moving at time 2. Right, and it begins to move backwards. So we plug in velocity at time 3. You get -3. Right, and this arithmetic's real easy here, right? Just plug 3 in here and 3 in here. So 3 minus 4 is -1. 3 minus 2 is 1. 3 times -1 times 1 is -3. So super duper easy arithmetic. And these endpoints are 0, so these are both just less than. So the particle moves forward for a while, and then it turns around and starts moving backward. And then we plug in just another point, just anything bigger than 4, right? You want to plug in points from the various intervals. That's called making a sign diagram. I didn't do the full sign diagram here. That's something that you learned in college algebra. So if you have questions about that or need help with it, let me know. But sign diagrams are easy to do. Okay. So here, the velocity at 5 is 9, so the velocity is positive when t is greater than 4. So the velocity is positive on the intervals 0 to 2 and 4 to infinity. So the way we're looking at it now is that there's no maximum time. So that's how you write it. And that's the answer. All right, let's keep going in this example. And let's find the total distance traveled by the particle during the first 6 seconds. So there's a lot going on here. So I'm going to back up, and we're going to use what we have here to solve this problem. So look at what's going on. It's moving forward between 0 and 2, moving backward between 2 and 4, and then it's moving forward again from 4 to infinity, but we're really just going from 4 to 6 for part E. So how do I find the total distance traveled from 0 to 2, 2 to 4, and 4 to 6? So the way you do that is you just remember that distance is always positive. So we need to calculate the distance traveled separately for when the particle is moving forward and when it's moving backward. So we want to know distance traveled on this interval, so you break it up into bits. And you just take the absolute value of all the bits. It's always like the new position minus the old position. It's always the absolute value of that. Right? Every distance formula you've ever seen, or even the slope formula, right, which is like change in y over change in x. Change in is always new position minus old position. And when you do distance, you just take the absolute value because it's positive. Now, these are already positive because the particle was moving forward on this bit and moving forward on this bit. But the idea is just put an absolute value on it, because for other types of problems, maybe you don't know if it's positive. That way, if it's negative, you get a positive number. And then you just evaluate it, right? So you can just go to your calculator and just plug in the formula for the function, right? So our initial function, let me go all the way back and show you here. So our initial function is this. You can just put this into your grapher, into your y equals, use the table, type in 0, 2, 4, 6, and you'll get all the numbers. So that's actually how I did this. But you guys know how to use a calculator by now, right? So when t equals 2, the particle had gone 20 meters. The particle started off at 0. So it moved 20 meters over this, moved 4 meters over this, and moved 20 meters over this. And you just simplify all that. Everything's positive, so it traveled 44 meters in total. It had, if you look at the entire interval 0 to 6, it only went 36 meters total. But you have to look at the time that the particle moved backwards as distance traveled. It has to be positive. So that's the answer to that one. And there's a nice little diagram that I made just to kind of give you guys, just to help visualize what's going on. Right? That even though the particle is moving backwards, it still counts as distance traveled. So its total displacement is 36 meters. Distance traveled, 44 meters. All right, let's keep going. Next one, find the acceleration at time t and after 1 second. So pretty much the same stuff we've been doing. The acceleration is just the derivative of velocity. So you just take the derivative of your velocity function. So you get 6t minus 18, so that's your answer there. Then just plug in 1. 6 minus 18 is negative 12. So the acceleration is negative 12 meters per second squared. So don't forget the units. You need the units. And that's how it works. So what are we doing with all this? We have acceleration, velocity, position. What does it all do? What does it mean? Well, let's graph everything together between 0 and 6. And let's see if we can figure out what's going on. So we've done stuff like this before, right? Earlier, section 2.1 and 2.2, we did stuff like this. But now we're going to take it a step farther. So the next question we want to answer has to do with when the particle is speeding up or slowing down. So here's our functions. So let's see if we can figure this out. So the blue one is the position. So it starts, it's moving forward when it starts, when the timer starts, but it's at position 0. And you can see that it turns around and starts moving backwards. So it's moving forward from 0 to 2, which means it's slowing down. You can see that the curve is like bending towards the flat. Remember, flat means 0. So this, the derivative of this, that's the slope, that's this. So the slope here is negative, right? Which means that the velocity is starting to slow down. And then it gets here and it starts moving backwards. Then it turns around right there and starts moving forward again. So where would you say that the particle is speeding up? So if you have a nice graph like this, it's easy to see. Here the velocity was 0. So the particle slowed down. Just imagine you're driving a car. Hit your brakes and start turning around, right? Well, when you start going backwards, you have to accelerate to increase your velocity in the negative direction. So we can see here that the curve is starting to bend away from flat. So it's speeding up. So we can see that it's speeding up here. But it has to turn around and go forward again. So hit the brakes again. So it looks like it's slowing down here. So if the curve is bending into a horizontal tangent, it's slowing down. If it's curving away from a horizontal tangent, it's speeding up. So it looks like here it's speeding up and here. So between 2 and 3 and between 4 and 6. The other places it's slowing down because the curve is bending into the horizontal tangent, right? So it's speeding up between 2 and 3 and between 4 and 6 and slowing down between 0 and 2 and 3 and 4. Again, notice the use of the square brackets for the endpoints because the particle is continuing to move, right? It's not 0. So what I want you guys to think about is what is going on with the other two graphs here in this shaded area and this shaded area. Do you notice something different about the green and red graphs here and here compared to the green and red graphs here and here? So that's something I want you guys to work on and think about. If you notice a pattern between what's going on between 2 and 3 and 4 and 6 with the green and red graphs, it turns out that that is always true. And same with the graphs between 0 and 2 and 3 and 4. What's going on with those graphs? What makes them similar? Like what makes a particle speed up or slow down? It turns out is based on the green and red graphs. So I want you guys to think about that. All right. So that's kind of like a challenge problem. Think about it, and if you have questions, let me know. All right, so that was motion of a particle. There's other applications as well. So I'll let you guys read through the notes because I'm not doing all of the examples in the homework. I'm only doing a few. But I'll let you guys read this stuff. We have electric current. So the charge is just moving current. Then we have a chemistry example. So I'm going to go ahead and do this one. It's a homework problem, but I'm going to go ahead and do it. So this is Boyle's law. If you took chemistry, you probably remember this. It just says that compressing a gas at a constant temperature, the product of the pressure and volume remain constant. So think about it, right? So if you push twice as hard, if you double the pressure, the volume of the gas gets cut in half, right? At a constant temperature, right? If you change the temperature, the volume will change as well. So we want to find rate of change of volume with respect to pressure. That's number one. Then we're going to do some more in-depth type stuff here on parts B and C. So I'm going to go ahead and read all these, and then we're just going to go through them. So for part B, a sample of gas is in a container at low pressure and is steadily compressed at constant temperature for 26 minutes. Is the volume decreasing more rapidly at the beginning or the end of the 26 minutes? So think about that. We're going to use the derivative to solve that. And then write the formula for isothermal compressibility in terms of P. I'll explain what that means when we get to part C. All right, let's jump in. So we start with PV over C. We want to write volume as a function of pressure. So we have to divide both sides of that formula by P. So now, because C is a constant, it's just a number, that now we have, it's a function, right? We have volume as a function of the pressure. So we can take the derivative of volume with respect to pressure. And of course, we use the quotient rule. And because C is a constant, this just totally goes away. This is just 1, right? The derivative of P with respect to itself is just 1. There's no chain rule. And so you get this negative. So this is 0. You get this negative. This is just 1. So you just get negative C over P squared. So that's the answer to part 1, to part A. Now, before we move into part B, I'm going to give you a way of thinking about part B. So part B is asking us to determine if we slowly increase the pressure, does the volume change more at the beginning or later on over the period of time that you increase the pressure, right? And that's what it says. Let me go back to, right? Steadily compressed at a constant temperature. So steadily compressed. So what I did is I drew a graph of the absolute value of the derivative, just because I didn't want to see a bunch of negatives, right? We just want to know, is the volume of gas changing faster early on in the 26 minutes or later on in the 26 minutes? Because the pressure is increasing steadily. I also divided by C just to scale the y-axis. C is a constant, right? So I just scaled it. So whatever that number happens to be, you can just multiply it out and it just stretches the graph. But the shape of the graph won't change. So this is a qualitative analysis, right? So we're using the derivative, looking at the shape of the graph, and seeing if we can determine the answer to part B. So what I want you to look at here is that let's go from like 1 to 2. So the pressure is increased from 1 unit of pressure to 2 units of pressure. What happens to the rate of change of the volume? Well, this graph here shows us the absolute value of the rate of change. So when P is 1, so 1 unit of pressure, the volume is changing fairly fast, right? Look at the slope. Here at 2 units of volume, the slope is less. The absolute value of the slope is less, which means it's not changing as quickly. Well, that's all we need to do to solve the problem. That's all we needed to look at. So the farther you move up, so the more pressure that's added, the slower the change in pressure is. We already know that the change in pressure is negative. So looking at the absolute value of the graph, I think helps us kind of understand qualitatively what's going on. You could easily have graphed this. That's fine, but it would be negative, and then you'd have to think about everything in terms of negatives. So it's easier just to do the absolute value. So the graph tells us that as P increases, the magnitude of the instantaneous rate of change of V with respect to P decreases. So V decreases faster at the beginning of the time period. And that's the answer, and that's all you have to say. Because we're just looking at the rate of change. How fast is the derivative changing, right? All right, next up, isothermal compressibility. So it turns out it's defined as beta. It's just negative 1 over V times the derivative. And it measures how fast per unit volume that V changes as P increases at a constant temperature. So it's a unitless measure, basically. So what we do is we're just going to plug everything in. We're going to plug in the formula for dVdP, and then we're going to plug in our original formula. We're going to sort of back substitute twice, and then we're going to simplify and see what happens. So you get negative 1 over v dVdP. dVdP is negative c over p squared here. But c is pv. So we've completely gotten rid of that constant. So we have a v in the numerator, v in a denominator. So we're sort of saying, doesn't matter what the volume is. We're saying per unit volume. So the volumes cancel. The negatives cancel. And one of the p's cancels. And you're left with just 1 over p. So the compressibility, how fast v changes as p increases, per unit volume. Right? So it's basically saying that it's an inverse function. How fast it changes. So it's pretty nice how this works. And that's the end of example 2. So you got one of these on the homework. It's basically the same as this, but I wanted to go over it because I think it's important to see not just physics examples over and over again. So you got a chemistry one in there. Here's some biology stuff. I'm not going over this example, but I want you to read through it. I'll let you read all that. I'm going to do, yes, another physics example. The reason I'm doing this one is because it's a different type of problem than what you've seen before. So Newton's law of gravitation says the magnitude F of the force exerted by a body of mass little m on a body of mass big M is given by that formula. So G is a constant and R is the distance between the bodies. So here R stands for radius. But it's just a distance, right? And it's the distance between the center of mass of the bodies. So let's find dF dr and interpret its meaning. Then we're going to talk about the minus sign. Then we'll come back and we'll look at part B. So part B just tells us that, let's say the Earth attracts some object with a force that decreases at a rate of 4 newtons per kilometer when R equals 30,000 kilometers. Right? So think about what it's saying. There's a lot going on here, right? So you can imagine that the object is moving away from the Earth, right? Because, well, we'll see in part A why it has to be moving away. And then how fast does this force change when the radius is 15,000 kilometers? All right, so let's jump right in. Let's look at part A. So there's our formula for the force. We're just going to take the derivative with respect to r. Of course, it's the quotient rule because our independent variable is in the denominator again. This one's really similar to the previous problem, right? This is a constant, so this is 0. Derivative of this is just 2r. And then you just simplify this expression, and you get negative 2g little m big M over r cubed. So this is how fast the force is changing as the radius changes, as the distance between the objects change. So what does that negative mean? Well, the negative basically means that whichever way r is changing, so if r is getting bigger, then the force is decreasing. But if r is getting smaller, the force increases. Okay? It just tells us that, that's the second one here. The change in force is opposite to the direction of motion, right? So think of it as like you have the Earth and then like a rocket escaping or something, you know. So, you know, is it harder for a rocket to escape the Earth's gravity when it's close to the Earth or farther away from the Earth? That's what we're going to answer in part B, right? But this gives us a clue. The derivative tells us something about what's happening with the rate of change of force. So for part B, we're told that this object that's 30,000 kilometers above the Earth is decreasing at a rate of negative 4 newtons per kilometer. Right? So for every extra kilometer it moves away, the force that the Earth exerts on it is 4 newtons less. Right? We don't need to know the mass. of the Earth. We don't need to know the mass of the object. We don't need to know the gravitational constant, because we're going to actually solve that stuff without knowing those numbers. So watch how this works. Well, we know the derivative, so we just set df/dr equal to the derivative, and we know the distance of the object from the Earth is 30,000 kilometers. So you plug in everything you know, and then we solve this expression for g little m big M, and you get 5.4 times 10 to the 13th. Don't worry about the units on this, okay? Because we're going to be using this to plug back into a different equation here in a second. This isn't the answer. If this were the answer, you'd have to put units. So look at what happened here, right? We know that this quantity equals -4. So you can solve this with algebra, or just some arithmetic, actually, right? And this is what you get. So then what we do is we set up the df/dr formula again. This time we know what GMM is. Remember, those are constants. We're talking about, an object escaping the Earth's gravity. So its mass doesn't change, the Earth's mass doesn't change, and g doesn't change. Plug in everything we know. So for the second part of the problem, we know GMM, right? It's 5.4 times 10 to the 13th. And we know the new distance is 15,000 kilometers. So this is pretty interesting, right? When an object is 30,000 kilometers above the Earth, and it's moving away, let's say it moves away 1 kilometer. On average, it loses 4 newtons of force as the Earth pulls on it. But look at this. When it's twice as close, so half the distance, the force exerted by the Earth is actually 8 times, right? As it moves away, right? The change in the force difference. The Earth only exists a force that would be 4 times as big, but this is cubed, not squared, right? So when you divide by r, the difference in r, right? So if it's like a half, but it's a half cubed, which is an eighth. So this is 8 times as big. You're dividing by an eighth. So pretty cool little problem. And one thing I want to point out is with all of these application problems, the units for the derivative always match the interpretation. So here we're talking about df/dr. So this is just change in force over change in distance. So the units on the final answer, if you get an answer for df/dr, has to match force divided by distance. So that number is sort of like the relative change. It's a proportion, actually, right? And then the units are always the units of the numerator and denominator. It always works that way. So if you're not sure what units to tack on, just look at the derivative itself. Force divided by distance. Well, newtons are force, kilometers is distance for this problem. So just to wrap up today, I just want to point out that we looked at lots of interpretations, right, of stuff. So velocity, density, current, power, temperature, gradient, and physics. We saw a couple of these. Didn't go over everything. Rate of reaction and compressibility in chemistry. Rate of growth, blood velocity, gradient, population dynamics. You have a couple of those on the homework. Marginal cost and marginal profit in economics. You have a couple of those on the homework. The marginal cost and marginal profit comes with its own video, so you can watch that video to see how this stuff works. Rate of heat flow in geology. Rate of improvement of performance in psychology. And rate of spread of a rumor in sociology. All of these ideas use the same concept, the derivative. Whether it's a first derivative, second derivative, doesn't matter. They're all special cases of this one idea. How fast is something changing? So if the position function is, some wiggly function, how fast is it changing at that point? So basically everything we've done so far in the class is about derivatives, so it's nice to get some applications. All right, well, that's it. For extra practice, got some nice problems here. One of your homework problems has you do the Explore It. I went ahead and put it in there anyway if you want to check it out first before you do the homework. But I think it's your second homework problem links right into the Explore It, which in turn links into what we saw in example 1 in these, in the PowerPoints. So if you have any questions, as usual, email me or post a question in the discussion forum, and I will see you guys next video. Bye-bye now.